Hello everyone, welcome to our lab 3. In lab 3 we're gonna go over two specific plots, the cumulative distribution function plot and the Q-Q plots. So in our previous lecture we went over histograms, bar charts, and even scatter plots. Today we're gonna continue analyzing numerical variables. So first, let's get started with an empirical cumulative distribution function. If you remember, in our last video, we discussed the probability density function or density plot. It gives you an idea of the shape of your distribution, right? It's useful to compute some probabilities. Now, in the case of the cumulative distribution function, the CDF, it's really interesting to analyze your data, especially when you want to see information related to quartiles, percentiles, position metrics. So this is a CDF. In the x-axis, you will have your variable, the variable of interest, and in the y-axis, you will have the cumulative probability. So what is the meaning of that? So for example, in this specific plot here, if you want to find what is the probability that x, our variable, is going to be less or equal than 6,000, right? So that probability is going to be this intersection here. So it's going to be around 0.3 and 0.4. Most likely it's like 0.35 using the CDF. Now this is useful when you want to see, okay, what percentage of your data is below or above one specific value. So it is interesting to make some decisions. So let me show you an example in a context that is familiar to all of you. In the first case study, let's talk about student grades. Okay, so a professor has recorded the final grades for 100 students in a data science course. These grades, they follow a normal distribution. The mean is 75 and the standard deviation is 10. The grades are from 0 to 100. Imagine that's like a percentage base. Okay, the professor wants to analyze the distribution of the data and answer some question. So first thing that we need to do is to generate our data. So grades, there are multiple ways to do this. Here we're using NumPy, NP, that's why you see this library here. And we get access to the random module, and over there you will find the different probability distributions. Now, you can generate numbers using different libraries. For example, SciPy is another alternative, which is also popular. Okay, so for the normal distribution, the first parameter is the mean value, and the second parameter is the standard deviation. So we get that information from the problem description, 75 and 10, and the size is the number of observations, n. So with this function, we're creating the grades, the 100 grades. The first line, the seed, actually it's not needed, it's not mandatory, but it has a purpose. When you're generating random numbers in any software, you need a seed. The seed is just an initial number to be able to generate the numbers that follow a specific distribution. Now, why in some codes you will see a seed? The seed, basically because if you set the same number here as the seed, then we should get the same results. So that's kind of like when you want to do something that is reproducible, that if you want to be like consistent, everyone's going to get the same thing. So it's important that you set the same, as a seed, the same number. It can be like 1, 2, 3, 100, 3, 2, 1. It doesn't matter which number, as long as if you have the same number as the other person, you will get the same numbers, the same results. Again, this is not mandatory. Okay, so now there are some questions. First, let's visualize the histogram and density plots to analyze the grades. Okay, let's do that. So using Seaborn, you can do histograms and density, but there is this plot which will show you the two of them, the histogram and the density plot. So you see the histogram with the bars, right? And we see the density plot. I want you to see if there is a problem with the density plot. Let me show you just the density plot. And please try to just pause the video 30 seconds, no more than that. And try to find if you see something like a problem with this CDF, with this PDF, because this is a density function. Okay, assuming that you pause the video, please notice that our variable, the x, it should go only from 0 to 100, right? But here, if you notice, the right tail, it's going above the 100. You see? So there is like a small chance according to the PDF. But in real life, according to our numbers, actually you see the histogram. Please notice that in the histogram that does not occur because the maximum value is not getting up to above the 100. So this is a thing that can happen with the probability density function. Just be careful in your analysis, right? Because in the real data it's not possible, right, to get a value above 100. Now maybe you're thinking if there is a bonus. I mean that's possible. If you define the variable then in that way, yeah, that's possible. But in general, that's not the case. All right. Now let's compute the CDF, the empirical cumulative distribution function. So we need two things. We need the variable, which we already have. We need to sort. We need to arrange that variable. And then we need to compute the probabilities, which we are going to find based on the ranking, on the positions of the observations. Okay, so let's do that. Okay, here. So for the x-axis, we need our grades. We need to sort the grades, right? So here with NumPy, we're sorting the grades, right? And then for the y-axis, we need to compute the cumulative probability. How? According to the position. So it will give you the probability up to that specific position. So let me show you what you get here. So let's print the grades sorted and the CDF of the values, the cumulative probabilities. So these are the grades sorted. So the minimum value in this specific case, for me, it was 48.8, right? And the maximum value, 93.5. Now, in the case of the cumulative probabilities, these are estimated based on the position of the observation. So for the first position, the probability that something is going to be below or equal to that value is 0.01, 1%, right? And it keeps increasing, right? Because it's a cumulative function. Then for the second observation, the cumulative probability is 0.02, all the way until we get the last one. It's 1, because always remember the CDF at the end is equal to 1. All right. So once we have our CDF, let's plot our CDF. So in the x-axis we have the grades sorted and the CDF value, the cumulative probabilities, right? And here these are just the markers. It's like how you want to see the points. The line style, no line, just the points. And the label is optional. It's like how you're going to label that information, so empirical CDF. The legend is just to show if you want to see the legend. You can label your axis, the x-axis and the y-axis, right? The title, if you want, for the plot, and the grid is true, just to show these lines here, the vertical and horizontal lines. They are useful especially when you want to compute some specific values. So this is how it works. This is our CDF. So for example, if you want to know like which percentage of the students got a grade below or equal 70, right? So you just go to intersection of your CDF and you will see that probably is around 0.3 or 30%. 30% of the students got a grade of 70 or less than that, right? But you can claim like you can do something similar with the complement. For example, you can say that around 70% of the students got a grade higher, right, or above or equal 70, right? That's also possible here in the analysis. Okay, now let's answer the questions. There are some questions here. The first one, find the median grade, and of course, do an interpretation. This is really important. I need to stress this a lot in the homeworks, assignments, during the test, and in life. it's critical, guys, that it's not this is not just data science is not just about coding. I mean, yeah, of course the coding part is important, but as we have these powerful generative AIs, ChatGPT now, we have DeepSeek and Gemini. I mean, the coding part it's getting easier, and we need to add value with the analysis, with interpretation. It's important that you just not provide not just the code, also you need the interpretation part. Okay, so let's find the median value. So how can you do that? We know that the median of Q2 splits our data set into equal parts, right? So 50% of the observations are above, 50% of the observations are below. So how can you use the CDF for that? So we find the 0.5, you can change the scale if you want, like because right now it's increasing like 0.2, 0.2 plus 0.2 plus 0.2. You can use like 0.1, that's fine. So 50% will be here, around here. And then if you go to the x-axis, you find that the grade is going to be between 70 and 75, I say. Right? Now you can compute the exact value. If you take your grades, using NumPy, you can find the median, like some percentiles. Or if you want to use Pandas, you can also create like a data frame, right? And compute the median value. Or you can describe the grades and it will show you the median value. So the exact value is 73.73. So we know that in that specific data set, 50% of the students got a grade above or equal than 73.73, and 50% got a grade below or equal 73.73. Okay, so now the next question is determine the top 10% cutoff. So what is the minimum grade required to be in the top 10%, right? The top 10%. So you need to understand first the question. Okay, so the top 10%, that's actually a percentile, the 90th percentile. So you want to find the 90th percentile because you want the grades that are above that value. So using Pandas, this is a quantile 0.9. That means the 90th percentile, right? From grades, you will get that is 85.02. We can see the plots here. So 90 is here in the middle. And we go down. Yeah, it's between 85 and 90 for sure. 85.062. Okay. The next question is a student scored 80 on the final exam. Using the CDF, find the percentage of students who scored less or equal than 80. Less or equal than 80. So this is 80, right? 80. So you go here, it's like 0.70 something, right? The probability that will give you the percentage of students. Now, if you want to compute that, we can count. So we check this condition, grades below equal 80. So what you get, if you just evaluate this data frame, column grades, and the condition less equal than 80, you will get true, true, false, true, 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 false, true, only for each row. You will get whether the condition is satisfied or not, if it's true or if it's false. Now if I sum that, it's gonna add all the truths, because truths are ones. Every single true is equal to 1, false is equal to 0. So what we're doing here is just basically counting how many observations are below equal 80. And then we just divide that over the total amount of grades. In this case, there are 100 students, right? So we get the 0.76 or 76%. So we know that 76% of the students got a score less or equal 80. If the passing grade is 60, what proportion of students fail the course? So it's similar here, like you count the number of students below 60 and you find the percentage. In this case, it's 6%. You can validate everything with the CDF plot, because that's the idea of this plot, to be able to check and to get an idea real quick of a percentile, of a cumulative probability. Okay, so let's continue. If scholarships are awarded to students in the top 5%, what is the minimum grade required to qualify? So this problem is similar to the when we were finding the top 10%, right? But here the top 5%, and that's the 95th percentile, and the exact grade it's 89.8. So you need a grade of 89.8 or more to be in that top 5%. If the professor wants to set a curve at the grade, should the professor place the A grade cutoff? What should be that cutoff? If only 20% of the students will receive an A. So if only 20% of the students will receive an A, that's this percentile, the 80th percentile. So we want to know, okay, which is that value. So grades above the 80th percentile, they are going to get an A. So here we're using the quantile method. We have the 0.8, right? And we get that the score is 81.65. Okay, so this is how you use. Now I believe that now you get an idea on how to use this cumulative distribution function. This is empirical one. This one. And now you can replicate the analysis in different contexts. For instance, here in case study 2, I will leave it to you. Just to give you an idea, it's about a company. They are analyzing information of 100 salesmen. Information is in thousands. Data for the sales follow an exponential distribution, not a normal like in the previous one. Here is an exponential. We have similar questions here, like analyze their data, some metrics, like what are the top performing salesmen, things like that. So we generate our exponential data, the sales for the 100 observations, and then we visualize the information. So let me show you something before I keep analyzing the cumulative distribution function. Please look at the density function. So we have the density function and the histogram, and I want you to stop the video. Just pause the video for a couple of seconds and identify what's wrong with the density function. Okay, so here our variable is x, it's sales, right? Sales. So in general, sales are going to be 0 or a positive number, right? It's not negative. But you see that the density function, since this exponential distribution is skewed, and most of the observations are here to the left, near 0. But there are no negative values. Actually, if you check the histogram, all values are 0 or positive, right? But the PDF, the density function, is a theoretical function. That's why it shows that there is a probability of getting some values below, some sales below 0, negative sales, which again in this specific case that doesn't make sense. So it's important that you always analyze these type of things and just be careful with your conclusions and your analysis. Okay, now this is the cumulative, the CDF, distribution function, and here you can even, if you want, you can add some lines like horizontal lines, vertical lines for a specific value, like the median value, like for 0.5, the cumulative 0.5. So you can get an idea of which value it is, and this is for the top 10% cutoff, the 90th percentile. You can do the same. So to get, that the sales are above 100K, right? Things like that. So the CDF is useful for this type of analysis. Again, I will leave it to you to complete the questions. They are pretty much the same thing as in the previous example, but using the new variable, sales. All right, now let's discuss our last plot, QQ plot in this video. So this is a quantile plot, and this is pretty much a scatter plot. But now you will see QQ plots every time in statistics. They are very common, especially when you are training models, let's say a linear regression model. There are some assumptions. you always need to check that your residuals or the errors, they follow a normal distribution. Or even in different contexts, sometimes you're analyzing a variable and you want to see if the variable follows a specific probability distribution. Then you can use Q-Q plots for that analysis. So the way they work is they have always a diagonal, like a straight line, and then you will see the observations, which are the dots or the points in the plot. Now, if the points, the observations are they have like a straight line and are like then they follow the theoretical distribution. But if you see that your observations they follow like a curved line, then it's not a good assumption that probability distribution. So let's do an example here. So for the Q-Q plot, there are different packages, different libraries where you can find the Q-Q plot. For example, in SciPy, I'm using this alias stats, but if you go on top of this notebook, you will see that we're getting this from SciPy. So in SciPy, we use stats, and the prop plot, it's a Q-Q plot, and the requirement, what are the inputs? Just the variable, the grades, or the sales. Then you need to specify which probability distribution you want to test. Typically, you will see the normal distribution because it's the most popular distribution, especially when you're testing assumptions, when you're checking assumptions. But this is not the only one. You can check whether your data follows exponential distribution, a different type of distribution. It doesn't have to be normal distribution. It can be any other continuous probability distribution. All right, so this is how a Q-Q plot looks. Again, you will see always this diagonal, this straight line, which is like the theoretical values. So the idea is that most of the observations, they should follow a straight line, or they should be on top of the straight line, right, on top of the diagonal. There are some deviations, right? That's normal, especially here in the corners. That's common, but most of the observations, they follow a straight line, if you see. What is the interpretation of that? It means that the grades, in this case, the variable grades, follow a normal distribution. It's a good assumption. It's a good assumption. Now, if we do the same for the sales, let's say you want to check whether the sales for the second case study, they follow a normal distribution. Please notice that now the behavior here is different. So the interpretation does not fall in our first interpretation, the straight line. It's a curved line. Then it means that data deviates from the theoretical distribution. You can see that, right? It's not a straight line, it's curved. That means that the sales, right, our variable, do not follow a normal distribution, which makes sense because remember that when we generate the data, we use exponential distribution. So here, if you change the parameter value, the distribution from normal to exponential, then of course you will see a straight line because it's the way it was generated. So these Q-Q plots, again, they are very useful. You will see them in every single statistical software, R, Python, MATLAB, StatGraphics, whatever you use when you're checking some assumptions in your residuals for models. So typically you use Q-Q plots for when you want to analyze the normality in your data. All right, I'm going to stop the video for today. I'll see you in the next session.